Welcome to section 1.1 on our journey with differential equations. In this first section, most of it is just going to be to verify that something is a solution to a differential equation. So in question 1 here, we have the first derivative is equal to 3x squared. And we want to demonstrate that y equals x cubed plus 13 is an actual solution. So we just have to differentiate x cubed plus 13. Well, the derivative of x to a power comes in the front, subtract 1 from the exponent. So the derivative of x cubed is 3x squared. Derivative of 13 is 0. And yes, this does satisfy this differential equation. In question 2, we have y double prime plus 25y, 256y equals 0. And they want us to verify that y1 and y2 are both solutions to this second order differential equation. So just to remind ourselves, we have a chain rule here. The derivative of the cosine of a function is minus sine of that function times the derivative of the stuff on the inside. So let's see, here's y1. I'm going to need y1, and I'm also going to need up to the second derivative. So differentiate it once by the chain rule. The 16 comes in the front. Differentiate it again, another 16 will come in the front. And the derivative of a sine is a cosine. And so now it's just a question of verifying. I'm going to plug in y double prime. I'm going to plug in y. So we've done that. And if I add these together, is that 0? Well, the answer is yes. Similarly, with our second solution, which is y2, we have the sine of 16x. So again, I need the original function, the second derivative, so differentiate by the chain rule. And if you look again, yes, it is also a solution to this second order differential equation. All right, in question 3 here, we have y prime equals y plus 16e to the minus x. And so they're giving us a y here. We need to verify that it is a solution. Well, the derivative for e raised to a function by the chain rule is e to that function times the derivative of whatever is up there. All right, so the derivative of 6e to the x is 6e to the x. The derivative of this e to the minus x, I get a minus in the front, so minus a minus 8 is a plus. And so we have all that we need to see if it actually works as a solution. So here's y prime. Here's the filled in for what the original y was, plus the 16e to the minus x on the end. Well, a minus 8 and a plus 16 is a plus 8, and yes, both sides are the same. All right, in question 4 here, we have 9x squared y double prime plus 99xy prime plus 225y equals 0. And again, we have two answers to verify. So the first one is y1, which is 1 over x to the 5th. I need to use my rules of exponents to rewrite this so that we can differentiate it. Because you don't want to use the quotient rule on that. All right, so looking at this, 1 over x to the 5 is x to the minus 5. Differentiate it, the minus 5 in the front, subtract 1, so a minus 6. If I differentiate it again, the minus 6 is times the minus 5, so a positive 30, and subtract 1 to get a minus 7. All right, so we've got all that we need. Let's fill this stuff in. Here's y double prime. Here is y prime. Here's my original solution. And so let's see, if you cancel the x's, all of these denominators have an x to the 5th in them. All right, question is if I add all this stuff up, do I get 0? Well, if you take the 270 and add 225, it is 495. So the difference would be 0. Now my second solution, y2, ln of x over x to the 5th. This is a bit uglier. Now to do the derivative of the second solution, you have two choices. You could leave it like it is, but then you're going to be stuck doing the quotient rule, which is often uglier. Or you can rewrite it as a product and then use the product rule. And so that's what I chose to do. I'm going to write it as a product rule. And so the product rule says the derivative of the first, which is 1 over x, x to the minus 5 sits there. ln of x sits, and now I'm differentiating x to the minus 5. So I got a minus 5 in the front, subtract 1 to get a minus 6. All right, and so that's what my y2 looks like when I clean it up a little bit. But I need to differentiate that again, so let's see. This 1 over x to the 6th is really x to the minus 6. And so when you differentiate it, you get a minus 6x to the minus 7. Now this stuff is again another product rule. So the derivative of the front part is 1 over x. The x to the minus 6 just sits there. All right, and then the ln sits there, and I'm differentiating x to the minus 6, and that's why there's a minus 6x to the minus 7. The minus 5 I pulled out in the front in the very beginning. All right, now let's try to clean that up some. So this is a minus 6 over x to the 7. Looking at this term, I have an x to the 7 on the bottom and x to the 7 on the bottom. So both of those are there. And let's see, I got a 5 times that 6, and it's a minus and a minus, so a plus 30. All right, I've got a minus 6 and a minus 5, so a minus 11 over x to the 7. Certainly much uglier than the first one. So now it's a question of plugging all that stuff in for y double prime, for y prime, and for y. And so with a bit of grinding and cleaning, let's see, this minus 99 term will cancel this term. I've got a 270 and a 225, but that will cancel the 495. And so, yes, we do get 0 equals 0. So a bit messy. In question 5, we want to substitute y equals e to the rx into our differential equation and try to figure out what would r need to be. All right, well, the derivative of e to the rx by the chain rule is r e to the rx. And so plug it in. Here's y prime, here's y. And so we start cleaning this up. Well, I'd like to divide by e to the rx on both sides so it cancels. Now, if you remember the graph for e to the rx, it's an exponential function. It's never zero for all values of x, so there's no problem with me dividing by that term. And so if we do that, we get 9r equals 11, or r is 11/9. All right, in question 6, similarly, we want to use e to the rx again, plugging it into this second order differential equation. First derivative, I get an r in the front. Second derivative, another r, so an r squared. And so, plugging all that in for y double prime, y prime, and for y, we get to this. All of the terms have an e to the rx in them, and so I can factor it out in the front. So I've got a product. I've got e to the rx times this thing is 0. But we just talked about that e to the rx is never 0. So the only way this product can be 0 is if this larger piece is 0. But that's a quadratic equation. And it's a nice one in that it factors. Minus 3 times 1 is a minus 3. The middle is a minus 3. Add a positive 1. And yes, we do get a minus 2. Setting each piece equal to 0, I get that the r that would work would either be 3 or minus 1. All right, in question 7, we have a first order differential equation. They're telling me what the solution is, and they're telling me also that y at 0 is equal to 3. So first we want to verify that it actually does work. The derivative by the chain rule, I'm going to get a minus 3 out in the front. So plug this in for y prime, plug in what we know about y, and so I got a minus 3c and a plus 3c. Yes, that is 0. All right, if I use my initial condition, which was y of 0 is equal to 3, we can figure out what this c must be. So y at 0 is equal to 3. All right, so plug in 0. Minus 3 times 0 is 0. But e to the power of 0 is 1. And so that tells me that c is equal to 3. So the function that solves our differential equation is 3e to the minus 3x. It does satisfy my initial condition, and if you looked at its long time behavior, it is a decaying exponential, and so over time it shrinks down towards 0. In question 8, they want us just to take the words and write a differential equation. So it says the slope of the graph of g, so slope is derivative, and is equal to the sum of x and y. Okay, well that's easy enough. And so I've got the derivative of y with respect to x is x plus y. All right, in question 9, there's a lot of verbiage here. The first part gives you what Newton's law of cooling is. So it's showing you how words transfer into symbols for the differential equation. There's Torricelli's law, which is the rate of change of water draining from a tank. We've got one for population. So the population is the rate of change of population is proportional to the amount of population at that time. And so finally, what is the question to all this? Well, if I have the time rate change of velocity of a coasting motorboat, it's proportional to the square of its velocity, and so we just write down the differential equation. And in question 10, we have the rate of change of the temperature of coffee at any time t. So temperature as a function of time is proportional, we have a proportionality constant. Okay, and it's proportional to what? Well, the difference between the temperature of the air, M, and the temperature in the coffee at a particular time. All right, in question 11 here, we have a population of rodents or rats, and they satisfy this differential equation, which says the rate of change is proportional to the square of the population. And so they're telling me initially that there were 2 rodents at time 0. And they're also telling me that the rate at which they are increasing is 1 rodent per month at the particular time when there are 10 rodents. That's important to note there because this is at a fixed point in time when there are 10 rodents. The rate is set at 1. All right. And they say that based on this kind of differential equation, that the answer looks like the following. Notice this answer has both a K and a K here with the T and a C. All right, so let's see. What do we have to do? So here's our differential equation. We know the population at time 0 is 2. And so we fit this model, plug in 2 for time. And so by doing that, plugging in 0 here, that means this term is gone. And so 1 over c is 2. And so I can figure out that c is 1/2. Okay. So let's see, what else do I know? Well, we know that the rate of change is 1 when p is 10. Okay, so p is 10, so I've got 10 squared here. All right, and 10 squared is 100, so k is 1 over 100. So if I fill in, what do I know? I know that c is 1/2. I know that k is 1 over 100. But this is kind of an ugly form to leave it in, so let's get a common denominator. Okay. So I pulled them together over the common denominator. If I have one fraction over another fraction, the top stays there, the bottom flips over. And so I get a formula that says that the population at any time is going to be 100 over 50 minus t. So this formula is valid for time being 0. And at time 0, notice we do get the initial population of 2. It's not valid when t is 50 because it would be undefined. And so that's why there's no equal there on the 50. And so what they wanted us to determine is what is the population going to be when we have 100? How long does that take? And when the population is 1,000, how long does it take to reach that number? All right, so what I did, rather than do this thing twice, I went ahead and got a formula. So P is 50, P times 50 minus T is 100. And so I can divide by P and I can get a formula for the time based upon whatever population we need. And so if P is 100, all right, I got 100 over 100. So this would be a time of 49 months. Because if you remember in the original problem, the rate was in terms of months. All right, if I plug in 1,000, then I've got 100 over 1,000, which is 0.1, so 49.9 months. And again, remember, the formula is valid only for under 50 months. All right, that concludes section 1.1.